Welcome, everybody, and good afternoon. My name is Abdeselam El Haman Abdeselam, and I'm a PhD student at ULB, working with my supervisors, Ivan Norte and Artem Napov. And today we are going to see how we ported an aggregation-based algebraic multigrid method to GPUs. So more precisely, what we are going to do is present a GPU extension of AGMG, which is an aggregation-based algebraic multigrid solver that is being developed in our numerical group in Brussels. So some motivations for this work are as such. First, as we have seen during this afternoon with other presentations, GPU is an emergent architecture, and we see more and more projects using this architecture. Second, AGMG is already known to be robust and fast, and has a black box interface, which is different than other multigrid methods. And we would like to see this performance in GPU. And also AGMG is already used by many users for diverse applications. So it would be great for them to use a GPU, the GPU port in those applications. So before continuing, I wanted to precise that this talk only discusses the solve phase of the solver for many reasons. Many applications of AGMG solve multiple times the same system, so only executed once the setup phase. And also, we benefit from the sequential optimal score tuning strategy that is done with a greedy algorithm, which is pretty sequential. So AGMG is, we can define AGMG by the following characteristics. First, it uses a Gauss-Seidel smoothing strategy, which is the to-go smoothing strategy for any AMG method. The consortium is based on plane aggregation with quality control on the aggregate to ensure robustness on the convergence of the method. It uses the K cycle, which is a W cycle with inner Krylov acceleration steps. And finally, the closest grid is solved with a direct solver. So now, in order to port this solver to GPU, we have to we face some challenges. First, the Gauss-Seidel smoothing strategy is not at all parallelizable. It's a pretty sequential algorithm. The K cycle requires dot product, which may impact its efficiency on GPU when used too much. And finally, there is no efficient sparse direct solver on GPU as such, and also the bottom grid is pretty small, so it will impact the efficiency on GPU. So first, we are going to face the first challenge, which, this will be the overlay of the presentation. So we are going to face each challenge one by one. And first, we are going to face the first challenge, which is the smoothing strategy. We present first the omega Jacobi smoothing strategy, which is defined as follows. It's a stationary iterative method where the preconditioner is the diagonal of the matrix. And also we use a relaxation factor here, the omega. So this method is okay for us, is parallelizable, so we can implement it on GPU. However, we want to keep the black box interface of AGMG, and it's pretty difficult to find an omega that works for all cases. So in order to fix that problem, we are going to use and present another smoothing strategy, which is the L1 Jacobi Smoother, which is defined as follows. Pretty similar to the Jacobi Smoother, but the preconditioner is a diagonal matrix where each element of the diagonal is the sum of all the elements of each row. And also we can see that there is no relaxation factor. With this method, we always assure convergence. Convergence is always guaranteed without any kind of relaxation, which means that the maximal value of the eigenvalues is smaller than 1. This will be used in the next slide. Now that convergence is guaranteed, we want to find a faster method, and this faster method can be obtained by using polynomial acceleration. So finally, we present the Chebyshev accelerated L1 Jacobi strategy, which is defined as follows, is equal to the L1 Jacobi. However, we use here a relaxation factor, and this relaxation factor, omega, is defined such as the damping is optimized for rough modes of the system, whose eigenvalues are in the interval 0.25 to 1. Why is that? Because we know, because L1 Jacobi is convergent, that the number of the the value of the eigenvalues are smaller than 1. So now that we have found the parallel smoother that we want to implement, in our case, we execute 2 iterations on the finest grid and only 1 in the coarser ones. So now that we have answered the first challenge, we're going to continue to the next challenge, which is the cycle. So multigrid cycles are defined based on the number of iterations on the recursive calls done at each level. So we have the V cycle, which is only one call of the recursive application. The W cycle is 2 iterations, and the K cycle is equal to the W cycle, only that we execute some inner quill of iterations at each level. So here you can see a figure describing the W cycle, how it works. So you can see that we have 2 calls at each time, at each level. And so, as we have said before, the K cycle has some potential drawbacks. So first, the dot product computing is not very effective because of the synchronization of the threads on GPU, and also it may be very expensive, the even W cycles in general, because the number of visits per level is exponential. So we spend more time on coarser grids, and we want to avoid that because the coarser grids are less efficient on GPU, because GPU we want the more data as much. So in order to address the first challenge, so the dot product computing, we are going to explore and present another cycle, which is derived from this one, and we call it the relaxed W cycle. The relaxed W cycle is a W cycle where the approximate solution is computed as such. First, we solve for the restricted residual R. We use this to smooth the actual residual. The solution, we use it to smooth the actual residual with a parameter tau, is a relaxation constant. And then we solve again with the second call of this W cycle. And in the end, we use both solutions to approximate our solution with again the smoothing constant tau. So this smoothing strategy is equal to the regular W cycle if tau equals 1. So in this case, tau equal 1.75 has been after extensive testing has been seen as the best parameter for symmetrical matrices. So now that we have presented the cycle, we have answered the second challenge, and the final challenge is how we are going to solve the coarsest grid. So the first challenge is that there's no efficient sparse direct solver for GPU. And so in order to solve this, we are going to use the already existing CPU solver. And we are going to see that we use a hybrid solver with GPU and CPU. So we are going to solve this on CPU, and also instead of direct solving this coarser system, we are going to execute a sequential version of AGMG on CPU, which is going to be faster than using a direct solver. And the second challenge is that GPU is not efficient when computing small systems. In order to do this, we are going to increase the size of the coarsest grid to 5,000 instead of smaller than was before. This is going to impact in the number of levels, so the exponential number of visits per levels is going to be a lot less critical. So here we can see a little overview of what happens on GPU and CPU. So these are on green, these are the finer levels, which are computed entirely on GPU. When we arrived at the restriction step, we copied the residual to the host memory. We solved the button system with either direct solver, or in our case, we approximate the solution with a sequential AGMG. And at the prolongation step, we copy back to the device memory of the GPU in order to continue computing these operations on GPU. So we have a hybrid structure, and it's not only GPU. So now that we have seen how we ported these three steps on GPU, we are going to have to benchmark this method. And for that, we are going to choose AMGX, which is the flagship solver from NVIDIA. And we're going to consider it as a reference in our study. So AMGX is the state-of-the-art AMG solver on GPUs, only GPU. And AMGX has many configurations and parameters in order to find a configuration that is close to our solver. So for this test, we have chosen two standards. So we have chosen AMGX, which uses an aggregation-based AMG configuration, and also a more classical AMG configuration. Both configurations use AMG as a conjugate gradient precondition and use the V cycle. We use the V cycle because it's the recommended cycle by NVIDIA, which works the best compared to the W cycle. So the numerical results have the following settings. So the maximum number, or the maximal number of iterations is 300. The relative tolerance is of 10 to the minus 6, and every test has been realized in a single GPU computer. So with a CPU at 4 gigahertz, 16 gigs of RAM, and the GPU, we use a 2080 Ti. So we can see the first results of our method. So before seeing the results, I'm going to explain the plots. So we have 4 different problems at each slide. We have 3 different sizes of the same problem here. On the x-axis, you can see the size of the problem. So it's going increasingly bigger. And we have, for each problem, 4 bars, which represent the time of execution of each method. The y-axis is actually the time of execution per second. The green bar is AMGX using an aggregation-based AMG method. The yellow one is AMGX using the classical method. And then the blue bar is AGMG with the relaxed W cycle that I have explained. And also the red one is the AGMG K cycle ported to GPU, so doing the dot product. So in this first slide, we have structured 2D problems. So the first one is a problem with constant coefficients. Here we have a problem with some discontinuities, and then we have some problems with anisotropies, and the last one is a problem with anisotropies, but is discretized by the bilinear finite element method. So we can see that in most cases, the fastest method is the AMGX classical method. But however, in the last one, in the bilinear finite element method problem, we can see that the method does not converge because it is known that these kind of methods do not converge very well on classical AMG methods. And for most cases, we can see that both of our implementations do pretty well compared to the AMGX aggregation-based method. So now we are going to continue with structured 3D problems. So we can see that we have more or less the same results. But in the bigger problems, we see that the methods, the AMGX methods tend to crash out of memory. And this happens often for very big problems. Then we continue to see unstructured problems, and here we see quite different results. So AMGX is also faster in the first problem. So these problems are L-shaped problems with local refinement in the borders of the L. And we can see that for the first problem, for the lowest degree problem, we can see that the AMGX classical is faster, but does not converge for higher degree problems, as well as the AMGX based on aggregation. And we have seen since the beginning that both of our methods, so the relaxed W cycle and K cycle, both are robust and always converge. So finally, we are going to see the results on unstructured 3D problems. So these problems represent a sphere on a cube where we have local refinement on the borders of the sphere. And the number here represents the degree of the discretization. So here we can see that again on the first problem we have AMGX which is faster, but then quickly diverges for bigger problems, as well as AMGX based on aggregation. And again, we can see that both of our implementations also converge with a similar number of iterations. So the last result that I want to share with you is that we compared our port of AGMG with the K cycle with the current version of AGMG on CPU. And we can see that we have very great speedups compared to the CPU version. I wanted to show you different problems here. So here we can see a structured 2D problem and a structured 3D problem, a unstructured 2D problem, and an unstructured 3D problem. In this one, we can see that the speedup is not quite big. Why is that? Because the size of this problem is not very big. This problem has a 8,000 more or less variables, and we have said before that the threshold of the cursor grid is more or less 5. So there's not a lot happening on the GPU. So that scales well for small problems because it's actually better to execute them on CPU. But in other cases, when the problem is big, we have very big speedups. So now that we have seen the results, and now that we have seen the results, we can see that we have developed a robust and fast hybrid GPU-CPU method. And both K cycle and relaxed double cycle have been implemented, and we have seen that their efficiency is pretty similar. So the fact of not executing dot products has not impacted very much. The relaxed W cycle is quite faster when the number of iterations is similar. We developed a robust smoother combining L1 Jacobi with polynomial acceleration, which is also fast thanks to this polynomial acceleration. And we have seen in the previous slide that it's 10 to 20, even 30 times faster than the CPU version. So this implementation also outperforms AMGX, which is a GPU-only AMG solver in terms of speed and also robustness. So when we compare it with the aggregation-based AMG, the aggregation-based AMG is robust, so it converges quite enough, but it's a lot slower. And on the other hand, AMGX with classical algebraic multigrid is faster, but is a lot less robust, as we have seen for problems with high degree. So in order to end this presentation, I wanted to share with you some objectives that can be derived from this work. First, the first objective is that we should work on the setup phase. So try to analyze core-setting strategies that keep the quality of aggregates with non-greedy algorithms. And also we should see a distributed implementation for multi-GPU architectures, because this implementation is based in single GPU machines. So thank you for your attention, and I would be glad to answer any questions.
Thank you very much, Abdeselam. And as you said, if there are any questions, now the time to ask them. Yes, Herbert.
Yeah. One question. Regarding the comparison CPU versus GPU, can you give a little more information of what you're comparing, a full CPU node against one GPU, or are you comparing one core of the CPU against the GPU? Can you give some data of the machines that you use as CPU and GPU?
All right. Yes, thank you for the question. So the machine is actually the same machine that we have. We executed every test on the same machine. So we used this CPU with an OpenMP implementation. So it's a multi-thread implementation of AGMG that we use on CPU.
Thank you.
Welcome. Thank you very much. I think that Gerhard also has.
Yes, Gerhard, go ahead.
Yeah, so my question goes along the same direction. So it is known that the RTX 2080 does not do very well on double precision floating point. So did you run your code in single precision?
No, we only it's a pretty straightforward port of AGMG. We tried actually to we had the idea to use mixed precision, but we did not implement it, or we did not go further with this idea. So we stood with the double precision algorithms.
So what is then the limiting factor? Is it memory bandwidth? Is it peak performance? Because when I see speedups, I always would like to know what is the bottleneck which gives us this kind of speed up.
Absolutely. The bottleneck, actually, the bottleneck of this method, we could achieve a bigger speed up, but the multigrid algorithm, instead of the linear operations like the matrix vector operations, the other operations are quite linear, sequential, and we cannot actually parallelize those kind of operations. For example, here we have like here, for example, we have many dependencies on the data. So this kind of operations cannot be parallelized, for example.
But you have the same problem on the GPU as well. So it should be even worse on the GPU if you compare with CPU. Exactly. So for that reason, I'm really surprised that you did get these high speed ups. And you also told that you have to do some workload on the CPU as well.
Yes. So actually, the thing that helped is that for the K-cycle, we joined many dot products and computed them at the same time. That helped a little bit. But what helped the most is that there is no many copies to between the host and the device, and also the increasing of the threshold of the CPU allowed us to profit to benefit of the size of the finer grids, because this is the biggest bottleneck is when you go on coarser grids, like for example here the grids become smaller and smaller, and while here is like 4 times smaller than this one, so we have 4 times a smaller occupancy on the GPU. So that's why we increased the threshold of the bottom grid.
So, and use the same grid then on the CPU, or do you adapt also your AMG to the specific feature of the GPU? Because there you can do much coarser levels and solve exactly at the end.
Yes. If I understood the question is, well, on the setup phase, so before the solving phase of the this method, we compute every level, every grid, and we copy this before the solve phase. And then during the solve phase, we do not compute any, we do not generate any grid whatsoever.
So your GPU measurements do not include any contributions from the CPU.
No, this time, every time, this includes all time during the solve phase. So the GPU.
But your comparison with the CPU, I'm just wondering to get 30 and 40x speedups again, because so if you carefully look at the numbers, you should be somewhere at 5 maybe. Mm-hmm. So I'm wondering why do you get a speed up of 30 or 40? So if you say we have reductions, we have to use the CPU at the courses level, and then suddenly everything is 40 times faster if you don't have those.
Yes, and to answer your question, one of the, well, we have analyzed empirically where we win the most time, and is actually on the smoother that we spend the last time, because when we compare with the sequential version or Gauss-Seidel, for example, in the K-cycle with the L1 Jacobi Smoother, you only do some math-vec operations which are pretty optimized for GPUs.
Okay, so but I'm still curious about.
Okay, all right, we can see this together.
Yeah, maybe we can continue this discussion later. Okay, thanks.
Thank you.
Thank you, Gerhard. I saw that Ulrich Friede had a question as well.
Yeah, hopefully a brief one. So one technique to analyze multigrid methods is through that textbook paradigm, which means that you're comparing your multigrid solve time with the work unit, which would be the matrix vector product. How much slower is your solver, say, compared to an optimized matrix vector product alone? So basically one application of the smoother.
One application of the smoother, if I recall correctly, because this was the first time of the project and I don't quite remember, but it was, if we compare it by eye, I don't have the numbers, but it was more than 10 times faster than the normal one, because we also in order to port it first on GPU, we actually implemented it on CPU, and it was there that we saw the big jump on speed up. So I don't have the numbers here by hand, but it was quite a lot at the time.
We may have to talk about that offline, but the classical way to analyze multigrid methods is in this work unit, which goes back to Archibrand. And then the textbook efficiency would mean you stay below 10 times the cost of a single smoothing step, and which is difficult to maintain in parallel. So, but it would be interesting to take a look at it from that perspective.
All right, thank you.
Okay, well, if that's it for the question, thank you very much, Abdeselam. If you could stop sharing your screen, please, we will be able to move to the next presentation.